Welcome to today's explainer. We hear constantly about AI software, right? Neural networks, algorithms, large language models. But today, we're actually unpacking the physical architecture of speed that's driving this entire boom. We're going to look at the foundational differences between the CPU and the GPU.
Okay, let's dive into this. 1.3 million individual components. It's just wild. That is what sits inside a single rack-scale machine today just to train a modern AI. But to understand why we need machines of such mind-boggling complexity, we first need to look at how microchips actually process information, and why relying on just one type of processing simply isn't enough anymore.
Part 1. Sequential versus parallel processing. These are essentially our two main characters for this explainer, the brilliant but solitary genius worker and the massive synchronized army.
First up, sequential processing. This is the traditional domain of the CPU. To really grasp this, think of the CPU core as a brilliant, solitary genius worker. It does one thing at a time, working through a list of instructions in strict order. Finish task A, then start task B. And because it has to handle everything sequentially, it's highly optimized to blast through that single instruction stream as fast and as cleverly as possible. We are talking incredibly sophisticated techniques here, things like deep pipelines, branch prediction, and out-of-order execution, all designed to squeeze out every single millisecond of speed for complex logic.
And this brilliantly illustrates the complete opposite end of the spectrum, parallel processing. Instead of one ultra-smart core doing tasks in sequence, the GPU trades a few brilliant cores for thousands of simpler ones. It literally operates like a massive, synchronized army. Now, why do that? Well, because graphics, and as it turns out, AI math, are full of identical, independent operations that need to be repeated millions of times. Training an AI is essentially just doing a billion simple math problems at the exact same time. So instead of one genius doing them one after another, thousands of small cores each knock out one simple task simultaneously.
Part 2. Comparing strengths and weaknesses. Let's set up a head-to-head matchup between our genius worker and our vast army of processors. Think about it like this. When your computer decides what happens when you double-click a folder, that is your CPU at work. CPUs absolutely excel at unpredictable branching logic and tasks with heavy dependencies. They run your operating system, power web servers, and calculate game logic. Basically tasks that require a constant shifting of gears. But when you need to calculate the lighting on a million polygons in a video game at 60 frames a second, that's your GPU. GPUs are built from the ground up for data parallel work, like rendering frames, simulating millions of physics particles, or, of course, training massive neural networks.
Now, what's really interesting about this slide is how clear the trade-offs are. The CPU clearly wins on latency, which just means the speed at which it finishes one individual task. Plus, it's a lot simpler to program because you don't have to coordinate thousands of simultaneous workers. But the GPU, it completely wins on massive, undeniable throughput. You scale it simply by adding more cores, rather than having to invent a smarter core, which gives you drastically better performance per watt for the right workloads. Essentially, the CPU is a nimble race car, while the GPU is a massive freight train.
But of course, neither is perfect. The CPU's throughput is strictly capped by that single instruction stream we talked about. If you give a CPU an embarrassingly parallel workload, you're leaving most of the chip completely idle, which is incredibly wasteful. Meanwhile, the GPU is just terrible at tasks with sequential dependencies, or heavy branching. If one simple GPU core is sitting there idle, waiting for another core to finish a task, you are wasting silicon. Not to mention, avoiding memory bottlenecks while trying to synchronize thousands of simultaneous workers is an absolute logistical nightmare, which honestly is probably why AI hardware engineers get paid so much.
Part 3. The unified rack-scale machine. We're pivoting from this rivalry to the ultimate team-up because modern technology doesn't actually choose between them anymore. So we have the CPU for complex, sequential logic, and the GPU for massive parallel math. But the real secret of modern cutting-edge computing is this beautiful synergy. The CPU acts like a conductor, handling the sequential, logic-heavy orchestration. It sets up the work, manages the memory, and basically directs traffic. Meanwhile, dozens of GPUs act as the heavy machinery, crunching through the parallel, data-heavy math that the CPU feeds over to them. They absolutely need each other to orchestrate massive AI workflows efficiently at scale. And to give you a sense of just how unbelievably powerful this synergy has become, consider 130 terabytes per second. That's the GPU bandwidth delivered in just one domain of the NVIDIA GB200 or GB300 NVL72 rack-scale system. To put that into perspective for you, that is enough bandwidth to literally download the entire Netflix library in a fraction of a single second. It achieves this mind-bending data speed by linking 36 Grace CPUs and 72 Blackwell GPUs together in a unified, liquid-cooled design.
And the scale here is only getting more extreme. Remember that 1.3 million figure from earlier? Well, that is the number of individual components you'll find inside the newly launched next-generation NVIDIA Vera Rubin NVL72. A single rack packs in 72 Rubin GPUs, 36 Vera CPUs, and 9 switch trays, delivering roughly 10 times more performance per watt than the previous generation. It's staggering, but this is the sheer scale required to push AI forward today.
Let's move to and see how this builds across the entire industry, because everyone is doing this. AMD's Instinct MI300A literally fuses Zen 4 CPU cores right alongside CNDNA3 GPU dies into a single unit with unified memory. Over in the cloud, the AWS Trin 3 Ultra server links 144 custom Trainium 3 chips for parallel processing that performs 4 times better than their last generation. Across the board, tech giants are completely abandoning the idea of the isolated chip and are instead building these fused, massive supercomputers.
And the result of fusing these CPUs and GPUs together? We are breaking computational barriers that were previously thought impossible. These exact CPU and GPU combinations are what's powering the fastest supercomputers on the planet. The Frontier supercomputer was the very first to break the exaflop barrier using AMD GPUs. And looking ahead, the El Capitan system is projected to exceed 2 exaflops of performance. And guys, this isn't just about faster gaming. This is world-changing computational power being used for discovering new life-saving drugs and accurately modeling global climate change.
So the crucial point is that none of these are really a GPU anymore in isolation. They are rack-scale systems that treat dozens of GPUs, CPUs, and ultra-fast interconnects as one massive, unified, parallel processing machine. The reality is, no single chip, no matter how perfectly designed, is big enough to train today's largest AI models alone.
We have gone from a solitary genius CPU to a parallel GPU army, to fusing millions of components into unified liquid-cooled rack-scale supercomputers just to keep up the pace. But physical space, energy, and cooling all have hard limits. So, since no single chip is big enough to train today's AI, what exactly happens to the AI revolution when we finally hit the physical limits of these massive rack-scale systems? It is the multi-trillion-dollar question. Thanks so much for joining this explainer, and we'll see you next time.